So in this video we are going to discuss the questions which appeared in CSIR JRF physical science examination that appeared in December 2018. So let's continue with the first question. The statement is the heat capacity CV at constant volume of metal as a function of temperature is given by the expression. So let's write the things which are given to us. CV, that is equal to alpha T plus beta T cube. Okay, so here alpha and beta, they are given to be constants. Okay, these are constants. The temperature dependence of the entropy at constant volume, so we have to evaluate the that how the entropy varies as a function of temperature for fixed volume condition. Okay, so from the second law of thermodynamics we know that we know that delta S, that is the entropy change between two equilibrium states, this is equal to ds from some initial state to final state, and then this is basically equal to ds, the definition of the entropy, that's dq by T, and this can be rewritten as dq for the constant volume process. We know that dq, this is given by Cv dt. Okay, and this is for the constant volume process basically. Okay, so this can be rewritten as from some initial state to final state, and then Cv dt upon T. Okay, let's call this as equation 1. Now we will make use of the given expression for the heat capacity at constant volume. Okay, so that means this is further equal to alpha T plus beta T cube divided by T and then dt from some initial state to final state. Okay, because here temperature is changing, so we can write here Ti to Tf. Okay, but that we will do at the end. Okay, so now this is further equal to temperature will cancel with temperature in both because in numerator and as well as in denominator we are having these quantities available. So this is further equal to alpha plus beta T square dt. Okay, or this can be further rewritten as alpha T plus beta T cube by 3, and then from some initial temperature Ti to Tf. Okay, so with this information we can write the delta S can also be written as S final minus S initial, that is equal to alpha into T final minus T initial plus beta by 3 T final minus Tf cube minus T initial cube. Okay, so now let's rearrange all the terms here in this expression, and then we will be we are almost at the our answer. So S final, which is in principle a function of temperature, so S final, that is equal to alpha Tf plus beta Tf cube by 3, and then I am taking Si to the right hand side, so Si, and then the terms with Ti. Okay, so that is minus alpha Ti and then minus beta by 3 Ti cube. Okay, so this can be rewritten as S final, that is S alpha Tf plus beta Tf cube by 3, and I am calling this quantity as some constant quantity where S0, it's going to be greater than 0 at at non-zero temperature. Okay, so SF, that is equal to, or in general what we can do is I can write this as S, which is a function of T. Okay, that is equal to alpha T plus beta TQ by 3 plus a quantity S0 that depends on the initial state of the initial equilibrium state. Okay, in principle the right answer should be this one, with S0 greater than 0. Okay, only in a special case when we are talking about the initial state at absolute 0, so then S0 it will turns out to be 0 in that case, in that particular case. Okay, but here if we take a look at the options which are given to us, so none of the option matches with our results that we have obtained. Okay, but now because if you just ignore the the initial conditions, so then the most appropriate results that matches with our answer is the option A. So therefore option A is correct here. So let's continue with the next question. The statement is the rotational energy levels of a molecule are EL, that is equal to h cut square upon 2 I naught in multiply by L into L plus 1, where L is equal to 0, 1, 2 and so on, and I naught is the moment of inertia. The contribution of the rotational motion to the Helmholtz free energy per molecule at low temperature in a dilute gas of these molecule is approximately. Okay, so we have to obtain the expression for the Helmholtz free energy, and that we can obtain by knowing the partition function for the given system. Okay, so let's try to understand how we can develop the partition function for the given situation or for the given system. So the energy spectra is given as EL is equal to L into L plus 1 into h cut square upon 2 I naught, where L is equal to 0, 1, 2 and so on, and I naught is the moment of inertia. I naught, it is the moment of inertia of the molecule. Okay, now the partition function is given by partition function. If you denote it by Z, because we are talking about the rotational partition function, so that's why I'm using a fixed rotational here, and this is equal to basically GL, where that represents the degeneracy of a level. Okay, exponential minus beta multiply by EL. Okay, and here GL, that is equal to 2L plus 1. Okay, so therefore the partition functions, it turns out to be equal to summation 2L plus 1, L taking value from 0 to infinity, and exponential minus beta multiply by EL. Okay, so minus beta h cut square upon 2 I naught L into L plus 1. Okay, so let's call this as equation 1 here. Now we will change the value of L1 starting from 0, and then we will write the different terms to obtain the partition function. So the first term, when L is equal to 0, so this term will become equal to unity, so that's a degeneracy. Okay, basically, so that is 1 exponential minus beta h cut square upon 2 I naught minus beta h cut square upon 2 I naught multiply by L into L plus 1, and that will ultimately become equal to 0. Okay, plus the second term, and when we put L is equal to 1, so degeneracy will become 3. 2 into 1 plus 1, that will give us a factor of 3, and exponential minus beta h cut square upon 2 I naught multiply by L into L plus 1. So when L is equal to 1, so this will give us a factor of 2. So multiply by 2 here, and the next term will be 2L plus 1, that is obtained with L is equal to 2, so that will give you a factor of 5. Exponential minus beta h cut square upon 2 I naught and L into L plus 1, that will give us a factor of 6, and plus so on, plus higher order terms. Okay, so here if we just because the factor beta h cut square by 2 I naught, it's common for all the terms, so if we just substitute, so let's say let beta h cut square upon 2 I naught, let's say this is equal to some constant C. Okay, so here not beta, we exclude the beta from here, so only h cut square upon sorry, 2, it is 2 h cut square upon I naught, 2 h cut square upon I naught, or you can say h cut square upon I naught, let's say that is equal to c. So in terms of that factor, so z rotational, it turns out to be equal to the first expression, it's 1 plus 3 exponential minus c beta plus 5 exponential minus 3 c beta, okay, plus so on. Okay, now if we just take a look at the expression, the term here, because we have to find the expression for the partition function at low temperature. Okay, so in that case, the this term, the terms 5 exponential minus 3 c beta and the higher order terms, they will decrease much faster than exponential minus c beta term. So that means we can neglect all other higher order terms, including this term 5 exponential minus 3 c beta and other higher order terms at low temperature. Okay, so in this situation, so therefore what we can do is we can write the partition function under this approximation at low temperature. Z rotational is equal to 1 plus 3 exponential minus c beta. I hope this point is clear, because see here exponential minus c beta can be written as 1 upon exponential c beta. Okay, and if you just compare this term with exponential 5 upon exponential it is 3c beta. Okay, 3c and then divided by kT. So for low temperature, when temperature is small, so this exponent, it will become a larger quantity. So when this exponential, it's a larger quantity, so that means 5 divided by this a large quantity, that will become a very small quantity basically. So that's the point that I just mentioned here. So that at low temperature, this term and other higher order terms, they will decrease much faster compared to this term. Okay, so we are here with the expression for the partition functions. Let's call this as equation 2 here. Okay, so we can substitute the value of c here, then this is equal to 1 plus 3 exponential, and c is h cut square upon I naught basically. Okay, so exponential minus h cut square upon I naught and then value of beta, which is kBt. Okay, so this is the partition function basically. Now the Helmholtz energy, it's connected to the partition function. The Helmholtz free energy, Helmholtz free energy is given as F, that is equal to minus kVt and multiply by logarithmic of partition function. That's the definition of the Helmholtz free energy. So if we substitute the value of the partition function from the equation 2, so this turns out to be F, that is equal to minus kT logarithmic of 1 plus 3 exponential 1 plus, it is 3, 1 plus 3 exponential minus h cut square upon I naught kT. Okay, and this can be further rewritten as, because if you just expand these terms, so ln1, that will give us a 0, and ln3 exponential this exponential minus h cut square upon I naught k. After expanding it, so we will obtain, this is approximately equal to minus 3 kT exponential minus h cut square upon I naught kt. Okay, so this is our final, and here just to let you know, so here we have made use of the fact that ln 1 plus x, this is equal to x minus x square by 2. So for very small value of x, so this can be neglected for small x. Okay, so we made use of this fact here to expand this ln 1 plus 3 exponential minus h cut square upon I naught kt. So therefore the Helmholtz free energy, this is equal to this expression. So if we just compare the with the option, so we find that the D is the correct option here. So let's continue with the next question. The statement is, the bidirectional motion of a diatomic molecule may be considered to be that of a simple harmonic oscillator with the angular frequency omega. Okay, if a gas of these molecules is at temperature T, what is the probability that a randomly picked molecule will be found in lowest bidirectional state? Okay, so let's try to find the the correct option out of the given 4 option. So here we can solve this problem by first knowing the partition function for this system, and then we will find the expression for the probability for the molecule to be in the lowest bidirectional state. Okay, so the energy eigenvalue for the harmonic oscillator, so energy eigenvalues for harmonic oscillator, they are given by En is equal to n plus 1 by 2 multiplied by h cut omega, where n can run from 0, 1, 2 and so on. Okay, and omega is the angular frequency of the harmonic oscillator. So by knowing the energy spectra of the harmonic oscillator, the partition function is given by the partition function for the this harmonic oscillator, that's given by summation running from 0 to infinity. Okay, so here I forgot to emphasize on one of the points. So because here the bidirectional motion of the diatomic molecule is given, so we are talking about the bidirectional motion of a diatomic molecule, and it is modeled as a simple harmonic oscillator. Okay, so that's why we are taking this energy spectra. Okay, so the partition function for the given situation, it is equal to exponential minus beta and then multiply by the energy spectra. And in principle we can always talk about the degeneracy factor here, but here since Gn, it will turn out that it is unity for all the energy levels here for the single oscillator, so we need not worry about this term here. Okay, so that means partition function is equal to, basically this is equal to n running from 0 to infinity and exponential minus beta multiplied by the En, which is n plus half h cut omega, and this can be further written as, you simply keep on changing the value of n. So this is the first term will be obtained when n is equal to 0, so that will give us beta multiplied by h cut omega by 2. So we can write it as minus beta h cut omega divided by 2. Now for n is equal to 1, the exponent will be exponential 1 plus 1 by 2, so that will give us a factor of 3 by 2. Okay, so this will be minus 3 beta h cut minus 3 by 2 beta h cut omega plus exponential minus 5 by 2 beta h cut omega plus so on. Okay, so now we will take a factor common from all of these terms, which is exponential minus beta h cut omega by 2. Okay, exponential minus beta h cut omega by 2. So we will take it outside, and then inside we are left with 1 plus exponential minus beta h cut omega plus exponential minus 2 beta h cut omega plus so on. Okay, now if you just take a look at the terms in the parenthesis, so this is basically a series with the common ratio of exponential minus beta h cut omega. So this is further equal to exponential minus beta h cut omega, and sum of the series is equal to 1 upon a minus r. So a is the first term, so that 1 minus common ratio, which is exponential minus beta h cut omega. Okay, so this is the partition function basically. Okay, let's call this as equation 1. Now we have to basically find out the probability of finding a particular molecule, a randomly picked molecule, in its lowest vibrational state. Okay, so the lowest vibrational state is given by when n is equal to 0, which implies E0 represents the lowest vibration state of the oscillator basically, or the diatomic molecule. Okay, so E0 is equal to h cut omega by 2. So therefore the probability of finding a molecule in this state is given by probability of finding a molecule in the state E0, that is equal to exponential minus beta energy of the level divided by the partition function. Okay, and this is nothing but exponential minus beta h cut omega by 2. Okay, the value of E0 and divided by the partition function, that the expression that we just obtained in equation 1, and this is equal to exponential minus beta h cut omega by 2 divided by 1 minus exponential minus beta h cut omega, and after we'll see that these two terms, they will cancel with each other. So therefore the required expression for the probability is 1 minus exponential minus beta h cut omega. So that is our answer here. So let's see which option matches. So it is the option A here. Okay, 1 minus exponential minus beta h cut omega. So this is A is the correct option. So therefore A is correct here. So let's continue with the next question. The statement is, consider an ideal Fermi gas in grand canonical ensemble at constant chemical potential. Okay, the variance of the occupation number of the single particle energy level with mean occupation number n var is. Okay, so let's try to understand this problem. The variance of the occupation number, that is the variance in n, which is the occupation number basically, it's given by the expression sigma n square, that is equal to kt dd mu of the occupation number. Okay, so here the occupation number for the fermion is given by the because we are talking about the Fermi gas. Okay, so we need to we should know the occupation number for the fermionic system, and it is given by the occupation number for fermion is this is equal to 1 upon exponential E minus mu upon kt plus 1, where mu is the chemical potential and E is the energy of any particular level. Okay, particular energy level. Mu, it is the chemical potential. Okay, so now we have to find out what is the value of sigma n square. Okay, so let's call this as equation 1 and this as equation 2. So sigma n square is equal to sigma n square, that is equal to kt d mu of n var, which is basically 1 upon exponential E minus mu by kt plus 1. Okay, so this is further equal to, so sigma n square, that is equal to kt as it is, and then the differential of this expression, and this is equal to minus 1 by x square, you can say, minus 1 by e power E minus mu by kt plus 1 its square, and then differential of the exponential factor. Okay, so that will come out to be exponential E minus mu by kt, and then it's with respect to mu. Okay, so this is equal to 1 by kt, minus 1 by kt, differential of minus mu by kt, so that will be minus 1 by kt. Okay, so minus and minus, they will cancel with each other, and kt and kt, they will also cancel with each other. Okay, so it will cancel with kt, and minus they will become plus. Okay, so this can be further rewritten as exponential e minus mu by kt can be written as beta times e minus mu, and here what I'm going to do is I'm adding 1 and subtracting 1. Okay, and then divided by e power beta e minus mu plus 1 and its whole square. Okay, and this can be further rewritten as, we are going to separate these terms. Okay, so 1 plus exponential beta e minus mu, we will keep it separate, and then divided by this the denominator, which is square of 1 plus exponential beta e minus mu. So one of the term will cancel, and we will be left with one single term, 1 upon e power beta e minus mu plus 1, and then minus 1 divided by e power beta e minus mu plus 1 its square. Okay, and this is further equal to n var. Okay, so because this is nothing but this quantity. Okay, n var, and then minus n var square. Okay, and this is further equal to, you just take n var outside, and inside we are left with 1 minus n var. Okay, so therefore if you just compare the options which are given to us, it matches with the option A. So therefore option A is correct here. A is correct. Now let's continue with the next question. So we are given the ground state energy of an isotopic harmonic oscillator, which is described by the potential Bxyz, that is equal to half m omega square x square plus 2m omega square y square plus 8m omega square z square in units of h cut omega is given by. Okay, so let's try to write the potential in its standard form. So the given potential Vx y z, it can be written as, this is equal to, the first term it's already in the standard form, so we have to simply make the manipulation for the second term and the third term, and then we will be able to figure out the ground state energy for the given anisotropic harmonic oscillator. Okay, so 1 by 2 m omega square x square as it is, plus the second term. So here what I'm going to do is I'm adding a factor of 1 by 2, and this will be adjusted in the numerator via term 2 omega its square and then y square plus 1 by 2 m multiply by 4 omega square z square. Okay, let's call this as equation 1 here. So if we just take a look at the equation 1, so here we can call this as the x, ex, ey and ez. Okay, such that the frequency of oscillation along x direction, this is equal to omega, and along the y direction we call it omega y, that is twice omega, and similarly omega z, this is equal to 4 of omega. Okay, so that's why it's a, in this sense it's a an harmonic oscillator. Okay, so now the ground state energy is given by, for the given potential, the ground state energy E nx ny nz, that is equal to nx plus 1 by 2 h cut omega x. Okay, and then plus the energy eigenvalues along the y direction, so which is ny plus 1 by 2 h cut omega y plus nz plus 1 by 2 omega z, omega z outside, 1 by 2 h cut, this should be h cut omega z. Okay, so this is the equation 2 gives the energy eigenvalue for the given oscillator. So for the ground state energy is obtained by substituting nx equal to 0, ny that is equal to 0, and nz equal to 0. And if you do that, the ground state energy E0 0 0 that is equal to h cut omega x by 2 plus h cut omega y by 2 plus h cut omega z by 2, and that is nothing but h cut omega by 2 plus omega y is equal to 2 omega, okay, plus 2 h cut omega by 2 plus 4, no, omega z is 4 omega, okay, so 4 h cut omega by 2, okay, so this will give us, it is 2 h cut omega, and then 2 3 and 3 plus 1 by 2 h cut omega, so that will give us a 7 by 2 h cut omega. So therefore the correct option here is 7 by 2. So let's continue with the next problem. The statement is, a particle hops on a one-dimensional lattice with lattice spacing A. The probability of the particle to hop to the neighboring side to its right is P, while the corresponding probability to hop to the left is given as Q, which is equal to 1 minus P. So we have to find the root mean square deviation delta x, which is given by this expression in the displacement after n such steps. Okay, so this is basically the problem related to the random walk problem in one dimension. So let's try to understand this problem. So we are given a situation where particle, it can move either, suppose this is the starting point, so either this can move to the right with a probability which is equal to P, or it can move to the left with probability Q, where Q is given to be 1 minus P. Okay, and the other information that is given to us, that is the step size. Okay, the step size, this is equal to A. Okay, and it's not unity basically here. A, it's not equal to unity as done in the book basically. Okay, the total number of steps basically they are given to be total number of steps, they are given to be n. Okay, and if we assume that steps to the right they are equal to n1, and steps to left, let's say they are equal to n2, and further the probability to right, this is equal to P. Okay, similarly we assume that probability to left, this is equal to Q, and this is basically connected to the probability to the right by this expression Q, that is equal to 1 minus P. Okay, now the net displacement to the right, okay, the net displacement to right direction, that is given by, if we denote it by x, that is equal to n1, that is number of steps to the right minus number of steps to the left, and multiply by the step size. Okay, and this can be further rewritten as n1, and then we can write n2 in terms of n1 and n, and that is n minus n1 and then multiply by the step size. Okay, and after rearranging all these terms, this turns out to be equal to 2n1 minus n multiply by a. Let's call this as our equation 1. Okay, now the deviation in x, so we'll make use of the standard definition of the deviation. So the deviation in x is given by, that is delta x, that is equal to x minus its mean value. Okay, so here we will make use of the value of x that is given by equation 1, and then let's try to evaluate what is this equal to. So delta x, that is equal to x minus mean x. Okay, x minus average x. So x is how much? That is this expression 2n1 minus n a, and then its average of the same quantity. Okay, so that is 2n1 minus n, its average a, and okay, and this is further equal to 2n1 minus n into a minus 2 average of n1 minus n a. Okay, and this can be further rewritten as 2 n1 minus n1 average multiply by a, because this n, that this term and this term minus will become plus, and that they will cancel with each other, and this is nothing but this is equal to twice a times delta n1. Okay, so therefore from here let's call this as equation 2. So from here delta x square and its average, that is equal to 4a square and delta n1 square, its average. Okay, and further this can be written as, because delta n1 square, if you remember the article that is done in the book by Reef, so delta n1 square it's already calculated there. Okay, so delta n1 square is basically npq. Okay, so this can be rewritten as 4 a square and then the value of delta n1 square, which is nothing but npq. Why? Because delta n1 square, so this result you have to remember, this is very nicely done in the book by Reef, so we are taking this result directly. In principle this can be proved also, but it will take a large amount of time here, so I'm making use of this result directly here. N p into q. Okay, so therefore RMS deviation in displacement is, that is delta x square which is further equal to x square average minus average x square, and this is further equal to 2a 2a and pq. Okay, so therefore C is the correct option here. So let's take a look at the next problem. The statement is the volume of an optical cavity is 1 centimeter cube. Okay, so let's try to write the things which are given to us. The volume of the cavity it's given to us, this is 1 centimeter cube. Okay, the number of modes it can support within a bandwidth of 0.1 nanometer. So basically we are given the information which we call as d lambda, and that is equal to 0.1 nanometer. Okay, and because the volume is given centimeter cube, so we can translate this information into centimeter cube also. So this is nothing but this is equal to 0.1 into 10 power minus 9 meter, and this is further equal to, in terms of centimeter, so this comes out to be equal to 10 power minus 8 centimeter. Okay, so what else is given to us? The centered at lambda is equal to 500 nanometer. So we are given the wavelength lambda, that is 500 nanometer, and this can be further translated into centimeter, and this will come out to be equal to 5 into 10 power minus 5 centimeter. Okay, now what is asked? The number of modes that can be supported. Okay, so as in the lectures in theory class, the number of modes, as we have done in radiation, in the chapter on radiations. Okay, the number of modes, so this expression you have to remember it. Basically, number of modes in a cavity of volume V in the wavelength range from lambda to lambda plus d lambda. So they are given by, number of mode is given by n lambda, it's denoted as n lambda d lambda. Okay, and this is equal to 8 pi V upon lambda for d lambda. So this expression you have to remember it basically. Okay, so now volume it's given to us, then d lambda, it's we have already written it in centimeter, and lambda also in centimeter. So what we have to do is we have to simply plug in the given values and then see what this number turns out to be. Okay, so therefore n lambda d lambda, that is equal to 8 pi into b. So because we have we have changed the entire information in centimeter, so volume it is 1 cubic centimeter, 8 pi v, and then divided by lambda 4. So lambda is this is 5 into 10 power minus 5 centimeter. Okay, 5 into 10 power minus 5, and lambda 4, so that means its power 5, sorry 4, and multiply by d lambda. So d lambda is how much? This is 10 power minus 8 centimeter, multiply by 10 power minus 8, and if you evaluate this expression, this will come out to be equal to 4.0 into 10 power 10. Okay, so therefore here the order, because we are asked the order, so it's the option C that matches with our calculation. So therefore C is the correct option here. So let's take a look at the next problem. The statement is the energy level accessible to a molecule have energies which are given by these three different values, that is E1 equal to 0, E2 equal to delta, and E3 equal to 2 delta, where delta is given to a constant. A gas of these molecules is in thermal equilibrium at certain temperature T. Okay, the specific heat at constant volume in the high temperature limits, so that is under this approximation, varies with temperature as. So basically we can solve this problem by making use of the partition function, and then by evaluating the average energy. Okay, so let's try to see how we can solve this problem. Okay, so first of all, let's draw the energy levels which are given to us. So we are having a 3 energy level system, E1, E2, E3, and the values are 0, delta, and then 2 delta. Okay, so the partition function for this system can be written as Z, that is equal to 1 for the first the ground state energy, that's exponential beta multiplied by 0, so that will give us 1 plus exponential minus delta by kt, or you can write it exponential minus beta delta, and the third term exponential minus 2 delta by kt. Let's call this as equation 1. Okay, now the average energy can be written as, let's say that E is the average energy, and this is equal to, so here we will make use of the definition of the average of a physical quantity where I, it's taking value from 1 to 3 because we are having only 3 energy level, and it's EI exponential minus beta EI divided by the partition function, okay, which is I from 1 to 3 and exponential minus beta EI. Okay, so this is further equal to, this can be written as, by substituting value of all energies here, so this is equal to the first energy value, that is E1. So I am writing first the general expression for the energy E1 exponential minus beta E1 plus E2 exponential minus beta E2 plus E3 exponential minus beta E3 divided by e power minus beta E1. Now the partition function e power minus beta E2 plus e power minus beta E3, and after substituting the values of all the quantities, so first E1, because it's 0, so 0 multiplied by anything, that will give us a 0 plus delta E1, that is delta exponential minus beta delta plus E2, which is 2 delta exponential minus 2 beta delta or 2 delta beta, whatever you write it, divided by 1 exponential beta E0 plus exponential minus beta delta plus exponential minus 2 beta delta. So this is the expression for the average energy. Let's call this as equation 2. Okay, now the heat capacity behavior can be determined by making use of the definition of the heat capacity, which is CV, that is equal to curly T of E. Okay, so basically here we will make use of the the general expression for the taking the derivative of a function of type fyg dash, that is equal to g f dash minus fg dash upon g square. Okay, so by making use of this fact, we can write the differential of equation 2. Okay, so this is equal to g, so g is, it's a denominator here, so that is g1 plus exponential minus beta delta. It's a slightly lengthy problem, but the final answer, it's very simple. Okay, plus exponential minus 2 beta delta, that is g. Okay, g multiplied by f dash. Okay, so f dash is, so that means differential of the numerator. So in the numerator we are having delta common, so I am taking delta common outside, and then the differential of the numerator, so first term exponential minus beta delta, and then the differential with respect to t, so that means delta by kt, its differential, that will give us a minus delta by kt square. Okay, so here exponential minus beta delta, and then this negative sign will cancel with each other, so it will become positive, so it will another differential of the exponent, that will give you delta by kv t square. So k, it's a Boltzmann constant here. Okay, now the differential of the second expression, plus 2 exponential minus 2 beta delta, and then multiply by 2 delta upon kt square. Okay, now gf dash, it's done, and then divided by gf dash and minus fg dash. We will have another term here, so let me write first the minus fg dash. Now minus now the numerator minus delta, it's the numerator now, and in the inside the bracket we are having exponential minus beta delta, okay, plus 2 times exponential minus 2 beta delta, okay, minus f into g dash. Okay, so g dash is nothing but, let me write it here, minus f into g dash, which is exponential minus beta delta, and then the differential of the exponent again. Okay, so minus will become plus, so it is delta by kt square multiplication, and then plus exponential minus 2 beta delta minus 2 beta delta, and then differential of the exponent. Okay, so this will be 2 delta upon kt square, okay, and then bigger bracket here, and also here in the we will have g square below these two terms. Okay, so g square is basically, that is 1 plus exponential minus beta delta plus exponential minus 2 beta delta, its square, and here also 1 plus exponential minus beta delta plus exponential minus 2 beta delta, its whole square. So basically it's a g f dash minus f g dash upon g square. Okay, now we will apply the condition that's given to us. So that means at sufficiently high temperature, so that means when kT kVT, it's much larger than the energy separation. So in this case, exponential minus beta delta, exponential minus beta delta, it can be approximated as 1 minus delta by kt, and also exponential minus 2 beta delta, this can also be approximated as 1 minus 2 delta by kt. Okay, so with this approximation, this expression can be further rewritten as, so again now we are expanding the exponential terms. So cv, this is this comes out to be equal to delta square, the common terms delta square upon kt square, and inside the bracket, okay, we will have 1 minus beta delta, okay, plus 4 into 1 minus 2 beta delta. Okay, so we are merely expanding the exponential terms. Okay, and then we will rearrange the terms 1 plus 1 minus beta delta. So this is basically 1 exponential minus beta delta, and then now the exponential minus 2 beta delta. So that will give us plus 1 minus 2 beta delta. So we are retaining only the first two terms, okay, because beta delta, it's going to be much smaller, so higher order terms can be neglected. Now the denominator, okay, so this is 1 plus 1 minus beta delta plus 1 minus 2 beta delta, and its whole square. Okay, now after the after the settling the terms, so this comes out, sorry, the second term minus the second terms, I forgot to write that is delta square upon kt square, and then 1 minus beta delta plus 2 into 1 minus 2 beta delta, okay, and then the second term 1 minus beta delta plus 2 into 1 minus 2 beta delta, okay, and then divided by g square, okay, which is 1 plus 1 minus beta delta plus 1 minus 2 beta delta and its whole square. Okay, so now after solving this expression, we will obtain, I'm writing the expression directly, so you can check it yourself. Okay, delta square by kt square, and inside the bracket, after solving these expressions, we obtain 5 minus 9 beta delta. Okay, so basically it's 1 plus 4, that will give us 5, and then 4 into 2, 8 beta delta, and then beta delta here. So that's this expression, and then multiply by 3 minus 3 beta delta, 3 beta delta minus 3 minus 5 beta delta, multiply by 3 minus 5 beta delta, and then in the denominator we will have 3 minus 3 beta delta, its square. Okay, and this can be further approximated as by neglecting the higher order terms. So this is approximately equal to delta square upon k t square, and then inside the bracket we will have 15 minus 42 beta delta minus 9 plus 30 beta delta divided by 9 minus 18 beta delta, and this is approximately equal to 6 by 9 delta square by kt square. Note that here we have omitted the terms which contain beta lambda square. While doing the multiplication, all the terms which contain beta lambda square we have omitted, and the reason is that because beta lambda, it's given to be beta lambda, it is much smaller than unity. Okay, so therefore from this last expression we notice that CV for this, the system which is given to us, CV, it's proportional to 1 by t square. Although this question involves a huge calculation, but the answer is very simple. So let's take a look at the options which are given to us. So 1 by t square, so therefore D is the correct option here. So let's continue with the next question. It is basically from the Ising model. The Hamiltonian of one-dimensional Ising model of n spin, where n is very large, is given by this expression here. Okay, so here the spins sigma I can take value either plus 1 or minus 1 depending upon whether it's aligned in the upward direction or downward direction, and J is given to be a positive constant here. Okay, so at inverse temperature, the correlation function between the nearest neighbor spins, so we have to find the value of this sigma I sigma I plus 1. Okay, so this problem is a little bit lengthy, so I will continue with the determination of the average value of a physical quantity. So if we just take a look at the general definition of the general procedure for finding the average value of physical quantity, that is, suppose x is a physical quantity, so this is given by summation xi exponential minus beta ei upon exponential minus beta ei. Okay, and summation over I both in the numerator as well as in the denominator. Let's call this as our equation number 1 here. Okay, now we will make use of this definition to determine the average value of sigma I dot sigma I plus 1. Okay, so we want to determine this quantity. Okay, so this is equal to, basically, if you just remember that this is nothing but this is the partition function basically. Okay, so sigma I plus 1, that is equal to 1 by Zn, because it's a n spin system, so that's why Zn. Okay, and multiply by sigma 1 taking value of plus minus 1, and then the next spin sigma 2 taking value of plus minus 1 and so on up to the nth spin n taking value of plus minus 1, and the quantity sigma I dot sigma I plus 1, and then exponential this term, then okay, this term exponential and then minus beta ei. So basically for n spins it will involve a summation basically, okay, for the n spin system. Exponential minus beta this quantity minus beta multiplied by h, so minus and minus that will become plus, okay. So this is equal to exponential I taking value from 1 to n minus 1. Here we are not taking the integral up to n, because basically it's under free boundary condition. Suppose we are having 5 spin system, okay, so we are considering the nearest neighbor interaction like this. So this way we will have four terms basically. So I taking value from 1 to n minus 1, beta ji, then sigma I plus 1. Okay, so this can be expanded further, so let me write it further here so that we can make use of the space completely. Sigma I dot sigma I plus 1 and its average value, that is equal to 1 divided by Zn and then 1 by beta and curly j of this quantity sigma 1 equal to plus minus 1, so on sigma n equal to plus minus 1, and the exponential summation I taking value from 1 to n minus 1 beta ji sigma I dot sigma I plus 1. Okay, and this can be further rewritten as 1 by Zn. So this here basically we have taken a differential with respect to j, and when we do this we will recover this expression. Okay, so 1 by Zn into beta and curly j of, so we can expand this expression inside the bracket. So this is basically summation sigma 1 sigma 2 equal to plus minus 1, and this is exponential beta j1 sigma 1 dot sigma 2, and then the second term, it's between the nearest neighbor interaction between the second spin and third spin, sigma 2 comma sigma 3 with value plus minus 1, and then the exponential term exponential beta j2 and then sigma 2 dot sigma 3 and so on. Then we can write the last term as summation sigma n minus 2 and sigma n minus 1 with values plus minus 1 exponential beta j n minus 1 sigma n minus 1 and sigma n. Okay, so this can be further written as 1 by Zn beta 1 by Zn beta curly j of sigma 1 sigma 2 so on sigma n minus 2 sigma n minus 1, and which are equal to plus minus 1, and then the exponential term, all the exponential terms inside the exponential beta, and then inside we will have J1 sigma 1 sigma 2 plus J2 sigma 2 sigma 3 plus so on J n minus 1 sigma n minus 1 sigma n. Okay, and this is equal to, so this can be written, this is basically the partition function for the n spin system. Okay, so Zn basically, so this is equal to 1 by Zn into 1 by beta curly j of Zn, which is a function of J1 J2 so on J n minus 1, and if all j are they identical, then we can replace it with simply j. Okay, let's call this as our equation 2. So therefore ultimately our problem is left with the determination of the form of Zn, so that how the partition function for n spin which are arranged in one dimensional manner, so how the Zn will look alike. Okay, so let's try to determine the form of Zn. So we are going to generalize this result for the given statement in the problem. So here for the first case, when we are having only two spins, let's say. Okay, so let me write here the possibilities, possible values that sigma 1 and sigma 2 can take, and the corresponding interaction energy. By knowing the interaction energy, we can write the partition function. So let me write the results here when for two spins. Okay, so that is sigma 1 and sigma 2. So either the sigma 1 can take value of +1, so that means aligned in the upward direction, and sigma 2 can also take +1. Other possibility is +1 -1 -1 +1 and -1 and -1. So this is basically equivalent to this type of situation when both the spins they are aligned in the upward direction, and this is equivalent to it's first aligned in the upward direction and second one in the downward direction, and this the other situation, this corresponds to this scenario, and here both the spins they are pointing in the downward direction. So here the corresponding interaction energy, which is given in the statement of the problem, which is equal to -j and then sigma 1 dot sigma 2. Okay, so then if we calculate this h value, so for this case, so this will come out to be equal to -j. Why? Because h, it's given to be -j summation sigma I dot sigma I plus 1. Okay, so here for the two spin system we will have h is equal to -j sigma 1 dot sigma 2. So -j multiplied by 1 into 1, so that will give -j here. Okay, so for the second case, -j multiplied by 1 into -1, so minus will become plus, so this will be basically +j. So let me do it the one case here. So for instance, h will be for this case -j sigma 1 dot sigma 2, and for the first case I am talking about this one, so this is equal to -j multiplied by 1 dot 1, so that is equal to -j. So that's what I have written here, -j. For the second case it's +j, and for the third case also it's +j, and for the last one it is -j only. Okay, so therefore the partition function for when we are having only two spins, so Z2 will be here we are having 2 microstates with the same energy and another 2 microstates with the same energy. So we can take the degeneracy factor of 2 for the each case. So the partition function will be twice exponential minus beta j plus twice exponential with this is for the positive energy, and for the negative energy we will have a beta j here. Okay, so this is equal to basically 2 times 2 multiplied by exponential minus beta j plus exponential beta j, and this is equal to 2 into 2 cos hyperbolic beta j. Okay, so basically I can write this as 4 times cos hyperbolic beta j. Okay, so this is Z2. So let's call this as our equation. Let me see what number I have already given. It's 2. Up to 2 I have already given. So let me call this as equation 3. Okay. Now let's try to generalize the result for the 3-spin system, and then after that we can write the expression for the n-spin system based upon our these two results. Okay. So the second case that I'm going to discuss with you, it's the 3-spin system. So when instead of 1 spin we are having 3 spins. Okay. Sigma 1, sigma 2 and sigma 3, and then the corresponding energy for this case. Okay. So here the corresponding Hamiltonian will be H will be minus J. I am keeping outside. So by keeping the nearest neighbor interaction in mind, so it will be minus J S1 dot S2 plus S2 dot S3. Okay, so these are the basically we are considering the free boundary condition. Okay, the possibility of the various spins alignment are so 1, 1 and 1. So that means all the 3 spins, they are pointing in the upper direction. Okay, so the corresponding interaction will be here. Let's see. So 1 into 1 plus 1 into 1, so that will be 1 plus 1 2, 2 times minus J, so minus 2J for the first case. Okay, so I'm not going to work out all the energies, but I will write them directly. So you can check it yourself. Minus 1 and minus 1. The next possibility is plus 1, minus 1 and plus 1. The next possibility is plus 1. This is the fourth case. Okay, plus 1 and then minus 1, minus 1, plus 1, plus 1, minus 1, minus 1, plus 1, plus 1, minus 1, minus 1 and then plus 1. The last option is minus 1, plus 1 and minus 1. So let me write the possible energy values. So minus 2J, for this case you will obtain minus 2J again, and for this case you will obtain a value of 2J, and then 0, 0, 0 for this case, and 0 for this case, and 2J for the last case. Okay, and all these values can be easily verified by making use of this expression. Okay, so now once all these microstates and associated energies are known to us, then we can write the partition function. Okay, so the partition function, because here we are considering a 3-spin system, so Z3 will be, okay, so we are having 4 terms with energy 0, so that means the degeneracy factor here, that is 4. Okay, so what I will do is 4 times exponential minus beta and multiply by energy which is 0, so multiply by 0. Now the second situation, now we are having 2 terms with energy plus 2J. Okay, so the 2 terms mean degeneracy factor of 2, and then exponential minus beta multiply by 2J, so minus 2 beta J. Okay, plus the last energy terms with the energy minus 2J, so that means degeneracy is 2 here again, so 2 exponential minus minus will become plus exponential 2 beta J. So this can be generalized further as, so this is nothing but this is equal to 2 multiply by 2 inside exponential beta 0 will give unity, 2 plus exponential minus 2 beta j plus exponential 2 beta j, and this can be rewritten as 2 multiply by exponential beta j plus exponential minus beta j and its square. Okay, and this can be rewritten as this is basically 2 cos hyperbolic beta j. Okay, so that means this is further equivalent to 2 and then multiply by 2 cos hyperbolic beta j power 2. Okay, or Z3 can be rewritten as Z3, that is equal to 2 and then multiply by 2 cos hyperbolic beta j power 3 minus 1. So let me call this as equation 4. So this is our result for the 3-spin system. Now if we compare the equation 3 and equation 4, okay, so we can generalize the result for the n-spin system here. So by using 3 and 4 implies Zn for n-spin system where n is very large. This is nothing but 2 multiplied by 2 cos hyperbolic beta j power n minus 1. So let's call this as equation 5. Okay, so now equation 2 and equation 5. What is our equation 2? So that's basically the equation that we developed for determining the average value of sigma I plus 1, its average. Okay, so by making use of equation 2 and equation 5, so I can write sigma I. So here 2 and 5 implies sigma I dot sigma I plus 1 is equal to 1 by beta into 1 by Zn and curly j of Zn. Okay, so this can be further rewritten as now we will substitute the value of the Zn here. Okay, so this is further equal to 1 by beta, and what is Zn? This is, it's given here to equation 5. So 1 divided by 2 into 2 cos hyperbolic beta j power n minus 1 and then curly j of Zn. So Zn, which is 2 into 2 cos hyperbolic beta j and its power n minus 1. Okay, so now we have to differentiate this result, and then we are almost close to our final result. 1 upon beta and then 1 upon 2 into cos hyperbolic beta j power n minus 1 and then its differential. Okay, so 2 as it is, 2 will come here, 2 multiplied by n minus 1 and then 2 cos hyperbolic beta j and its power n minus 2 and then the differential of 2 cos hyperbolic beta j, which will be 2 sin hyperbolic beta j and then again its differential. So that will with respect to j, so that will give you multiply by beta basically. So this beta will cancel with this beta, and after the cancelling the sum of the common terms here, so we are left with n minus 1 multiply by 2 sin hyperbolic beta j upon 2 cos hyperbolic beta j. 2 will cancel with 2, and here for very large value of n, so this result is almost equal to n tan hyperbolic beta j. Okay, so therefore the correlation function per spin it's given by that is sigma I dot sigma I plus 1, so that is equal to n per spin, it is given by n tan hyperbolic beta j divided by the total number of spins. So n will cancel with n, so this is nothing but tan hyperbolic beta j. So therefore our answer is tan hyperbolic beta j. Okay, so in this question it took quite a large amount of time. So basically it's better to, if you can just remember the partition function for the n spins which are arranged in a one-dimensional manner. Okay, so then you can work out this expression quickly. So if you just take a look at the options which are given to us, so it's the C which is correct here.